Have you ever been to an amusement park and been on a ride that does something like this? Pretty exciting, isn't it? Maybe you've wondered, how is it that people stay in their seats? Now, of course, I've been on these and I know that you're strapped in like crazy to the point where it's practically painful. But on the other hand, if the straps weren't there and the train keeps moving, you know from the pressure you feel of being pushed down in your seat, which when you're upside down is technically up, you know that you wouldn't be moving out of that seat anyway. There's something keeping you there. Well, that's what our discussion is about today. Perhaps you've thought of that as centrifugal force. We're going to discuss that in a lot more detail in a moment. So, welcome to our discussion of circular motion. Let's start with a circle here that has a radius of r. And let's suppose that an object is moving right there in that direction at that particular moment in time. What do I mean by an object? Well, the idea is there's a thing here. Maybe it's a ball on the end of a string. Maybe it's something moving around a track and so on. Kind of got ahead of myself there. But at this particular moment, it's moving at a velocity of v. Don't forget velocity is a vector. So it has both a magnitude and direction. But a moment later, it's moving at the same speed, but a different direction. Maybe we'll call that the initial velocity. We'll call this the final velocity. So let's copy some of these vectors. Well, let's start with the radius vectors. There are two of them there. Of course, they are in different directions, but again, they are the same length because that's the nature of a circle. If we look at how we change from the initial position to the final position vector, that changes in that direction. Think about how vectors add, okay? We have the initial vector plus the change equals the final, right? And so this is the change in the position vector right here. We'll call that delta r. Again, technically that's a vector and should have a little vector symbol on top of it if we want to be truly accurate. So we could do it like that. Magnitude the same, direction different. Well, it turns out we can draw a very similar, and I mean that very literally, triangle involving the velocity vectors. We have our velocity vectors, initial and final, and our change in velocity vector, okay? And that's what I want you to focus on. We have the initial velocity plus the change in velocity gives us our final velocity. Isn't it odd how the change in velocity is a different length and different size, or different length and different direction completely? What I want you to notice about these two triangles is that when I said they're similar triangles, I mean that quite literally, because this angle in here is the same as this angle here. These two are not the same length as these two because, of course, they're not even in the same units. One's in meters and one's in meters per second, for example. But they're both isosceles triangles with the same vertex angle, so they are in fact similar triangles, which means we can set up proportions of similarity based on what we learned in geometry class. So, for example, r over delta r, that would be long side over short side on one triangle, is equal to v over delta v, long side over short side on the other triangle. Okay? So that's the proportion that we're going to start with to work our way through this problem. Now, as it turns out, if we look at the arc length S, which just magically appeared on your diagram right here, that arc length is, of course, curved. But as it gets smaller and smaller, it can be more and more closely approximated by a straight segment, what we would call a chord of the circle. Okay? That is, S can be approximated by delta R. And S, of course, is the distance that's traveled in a given amount of time at the given velocity. Please remember that if we're talking about a uniform speed, that the v here, oops, let's try that a little bit better, that the velocity, the speed I should say, is constant. The velocity is most certainly not constant because the velocity is changing direction all the time. So the vector is not constant, but the speed, the magnitude is constant. And s is equal to vt, distance equals rate times time, but s in very small increments can be estimated by delta r. So in the top equation, I'm going to replace that delta r with vt, and we get this. Now, if you do a little rearranging of everything, you can get something like this. You can get v squared over r is equal to delta v over t. But delta v is change in velocity divided by time, and that's acceleration. Okay, so we've defined an acceleration. Now the question becomes, what is the direction of the acceleration? Well, the direction of the acceleration has to be in the same direction as the change in velocity, because time doesn't have direction. Time is a scalar. Look at the change in velocity vector. It's pointed up and to the left. From down here, it's pointed up and to the left. That's toward the center of the circle. Isn't that neat? So the acceleration is toward the center. Now, if you think about it, this makes perfectly good sense. It has to be, if we're moving at constant speed. Here's why. If there was any component of the acceleration that pointed forward, then the object would speed up. If there were any component of the acceleration that pointed backward, then the object would slow down. The only way to maintain a constant speed is if that acceleration vector is pointed directly toward the center of the circle. That way it's perpendicular to the actual motion, and so at that moment doesn't change the speed. Make sense? Okay, that's why this works. And so we define something called centripetal. Note, I didn't say centrifugal. Centripetal, or center-seeking, which is what the word means, acceleration, which means acceleration toward the center of a curved path. And we've already developed the formula for that. The centripetal acceleration, which is an inward radial acceleration, is velocity squared, speed squared divided by the radius. Now, if you want to check the units on that, it's worth noting that speed squared would be in meters squared over seconds squared divided by the radius, which is in meters, for a final unit of meters per second squared, which is exactly what we want for the SI unit of acceleration. So this is how you find the magnitude of the centripetal acceleration. This is not a vector symbol. This is a magnitude. The direction is given in the name. It's toward the center, which means the direction is changing all the time as the object moves around the circle. Let's do a quick example. A 1,200 kilogram car is moving around a corner at a constant speed of 25 kilometers per hour. If the curve has a radius of 40 meters, what's the acceleration of the car? Now, at face value, you might be thinking, well, it doesn't have any acceleration because it's moving at a constant speed, right? Except that it's changing direction. I didn't say that it was moving at a constant velocity. The velocity vector is changing, so by definition, there has to be an acceleration because that's the only thing that can change a velocity. Okay? So now we have to figure out what that means. Our usual process might be to sketch a diagram of this and list some variables. Let's use the usual process. So here's a diagram. It might be a little bit hard to see there, but you can see what I mean about the car entering a curve. The entire circle wouldn't typically be there on the road, just the quarter circle that represents the curve, but you can see what I mean when I talk about the radius of a curve. So let's list some variables here. The speed is 25 kilometers per hour, which I've handily converted for you to 6.944 meters per second, so that the units match with the radius, which is 40 meters. So let's find the acceleration. Well, it's actually straightforward, as simple as it looks. The acceleration is the speed squared, 6.944 squared, divided by the radius. And that's it. All you have to do is grab your calculator and make a computation. I'll wait while you do that. Okay, you're back. My little pointer says that it's 1.2 meters per second squared. Now, that's the magnitude of the acceleration. The direction of the acceleration is toward the center. So if the car is, say, right here in its turn, okay, as it's turning around this way, it's accelerating toward the center. That way the acceleration doesn't change the velocity, or doesn't change the speed, but it does change the direction. That's how it works. Okay? Now, what about that word centrifugal force? For example, if you're in that car as it's moving forward, wouldn't you feel like you're being thrown to the left side of the car? Yeah, that's exactly how you'd feel. And we call that force throwing you to the left the centrifugal force. But I want you to understand what's actually happening. This is a pretty picture. I thought it'd be nice to look at. If you imagine entering that curve at 40 kilometers per hour, you're going to be feeling like you're thrown to the right. Okay, here's the back end of the car, say, right here. The wheels. Am I an artist or what? Okay, here you are inside. Give you some hair. I don't have any. So when you go around that curve, you feel thrown to the right. But what's actually happening is the car is accelerating toward the center of the turn, which is which way? That's right, it's to the left. So the car is accelerating to the left, and the seat of the car is attached to your bottom by friction, and so your bottom is yanked to the left also with the car, which means because of the inertia of your upper body wanting to continue moving in a straight line, your upper body is tilted over to the right. From your perspective, it's actually just going straight ahead while the bottom is moving to the left. So you feel like you're thrown to the right, but that's an illusion. What's actually happening is the bottom part of your body is being taken to the left and you're tilting over onto your right side. That's what we call centrifugal force, and sometimes people call centrifugal force a fictitious force because it's centrifugal force that actually makes things move in circles. Okay? Of course, from your point of view inside the car, it's not very fictitious at all. You feel it happening. But to the outside observer, everything's being pulled to the left, not to the right. And now you have the basic understanding of centripetal acceleration and centrifugal acceleration.